All right. This is worksheet 15.1. Let me just make sure my audio's on. Yes, my audio's on. This is my second time doing this worksheet because the first time I recorded it, I forgot to turn my audio on, and then I gave up for a week. So we're back here now. Let's just start with number one. So we want to evaluate this double integral without using an iterated integral. Okay. So whenever we are evaluating a integral without using an iterated integral, we need to sketch it and then give some geometric argument by identifying it as the volume of a solid like it says here. Okay, so first we sketch our region R. That's going to be the base of our solid, the base of our the base of our solid that we're finding the volume of. This notation here means that in the x direction we have an interval from 0 to 1, something like this. And then the y direction we also have an interval from 0 to 1. So the base is a 1 by 1 rectangle. I'm just going to redraw that again, so that's going to make it easier. Or no, I'll keep it like that for now. Okay, so this is the base. And then the actual integrand here is going to be the height of our function. And so whenever we're setting up a 2D integral like this region R here is the base of our solid. This right here is the height of our solid. Okay. And so I'm just going to sketch what this looks like. So this is I'm going to say that this is Z and this is Y. And because we're always going to plot Z equals whatever this is. So here Z is equal to 4 minus 2Y. That'll give us the height of our solid. If we plot this, we'll get something like this, where this intersection is 0, comma 4, and this one is 2, comma 0. Okay? And so this gives us the height of our solid. Now we just combine these two. The base is a square. That's 1 by 1. And then the height, well, in the x direction it's constant because our z is a function of x and y, doesn't have an x in it. And so as I change x, the height of my solid is going to stay the same. But in the y direction, it slopes downward like we saw over here. In particular, when y is 2, z is down at 0, but y only goes up to 1. And when y is 1, z is equal to 2. And so we have something like this. Okay. And now we have to find the volume of this region. Just again, this height is 1 because we said that when, this height is 2. Because we said that when y is 1, z is equal to 2. And then this height is 4 because the maximum height of z right here is 4. And so that's sort of what we have right here. I think it's good to try to make sure you know how to draw these. This is how sort of my thought process going through drawing them. Maybe you have one that works better for you. One thing you can also do is just plug in all of the vertices. So here I only sort of plugged in one, but you can plug in all 4 of the vertices of the total solid by plugging the 4 vertices of our rectangle into this function up here for z, this one up here. So for example, I could say when y is 1, x is 0, which is this vertex right here. No, this vertex right here. Y is 1, x is 0. Then z is equal to 2, which is why that one goes up to 2. And so you can also do that. Okay, anyway, now we need to find the volume of this region. So this will be the volume of the cube, which is basically, I'm going to split this up right here in half so that the bottom half is a cube plus the volume of the triangular prism. The volume of the cube is length times width times height, which is 1 times 1 times 2. So that's just 2. And then the volume of the triangular prism is half of that, because it's the volume of the triangle is 1/2 base times, or I guess width times height, and then you multiply by the length of your prism to get the total volume. So this is plus 1/2 times 2. So this will be 3 in total. And that is going to be this problem. I don't think I have any more comments, so let's move on to number 2, which is maybe a more important problem. Actually, this one's not too important either. Okay. So we're given this integral where r is equal to this. So once again, I'm going to start by drawing the base. R goes from 0, 4, which means x can be between 0 and 4, like this. And y can be between 0 and 2, like this. Okay. And so I'm just going to draw that. I'm going to shade it in. So that's my region. That's the base of my solid. Now I have to do the height, which is always going to be the integrand. And so the height is square root of 9 minus y squared. We say base. And then for the height, this was x, this was y. Again, since the height is only a function of y, I'll draw this in a zy plane. So let's see. I know that z is equal to root 9 minus y squared. If you square both sides, you'll get z squared equals 9 minus y squared. And so z squared plus y squared is equal to 9. Okay. So if you don't recognize this, this is a circle of radius 3. So it'll be something like this, where this vertex is 3, 0, and this one is negative 3, 0. Okay. And so now I just combine these two. And okay, I'll start by drawing the base. So it's really long in the x direction and not as long in the y direction. And then when y is 0, so that's along this line here, y is 0, then I'm right here. So my height is equal to 3. So I'll go up here. And then when y is, let's see here, this was what? 4, 0. So this vertex up here is 4, 2. And when y is 2, we can plug it into this formula or just find it on this graph. We'd see that z is root 5. So that would be somewhere up here. And then it'll be the same thing over here. And because it's a circle, it'll curve downward like this. And so that's what our region looks like. It may not be easy to see, but it is curved a little bit there on the top. This is a curve. If we want, we can go to Desmos. Let me just make sure that... Yeah, okay. We can go to... Ignore this. This is just my homework for another class. Desmos 3D. And then let's just graph this region. 9 minus y squared equals z. Oh, did I do that right? Oh, square root 9 minus y squared. Okay. And so yeah, it looks like that. And then again, we said x goes from 0, 4, and then y goes from 0 to 2. And so yeah, it looks something like that. It's curved downward a little bit, but not a whole lot. And it's long in the x direction. Okay. What might also be useful is instead of restricting the bounds of our region like that, we might also want to say, okay, let's plot it between the region x equals 0, x equals 4, y equals 0, and y equals 2, not x, y equals 2. This should be y equals 0. Okay. And it's that region inside all 4 of those rectangles. Granted, the rectangles do make it a little bit harder to see. If we want, we can try to make it a bit easier by adding these things up here. So let's see. And then here we can say x greater than equal to 0, and then 4 greater than equal to x greater than equal to 0. So that might help, and now we can only see the parts of the rectangle we care about, and the volume is the area inside this rectangle and under the red curve. So hopefully this lets you visualize that a bit. I wonder if we can do like z less than or equal to square root of 9 minus y squared. No, that didn't do anything. Okay. Maybe if I add it here. Nine minus y squared. Does that do something? It does do something. Okay. So you can play around with this, adding these braces to impose more constraints like this. And then you could, I guess, do the same thing on the red curve to get the region without any of this excess stuff, but I think that's enough exploring that for now. Now let's do some actual integrals on number 3. We want to find this double integral where r is this rectangle. Okay, so whenever we do one of these problems, we want to start by asking ourselves, do we want to integrate with respect to x first or y first? Here it doesn't really matter because if we integrate with respect to x first, we can do a u sub to do that integral. And if we integrate with respect to y first, it'll just be some power rule. I'm going to do x first because it's harder and I want to get it out of the way. So I'll put y on the outside and x on the inside. Xy squared over x squared plus 1 dx dy. Okay, so now we're going to do this first integral here. And remember, when we are doing integrals of, or I guess iterated integrals, we always do the inside integral first, but we treat all other variables as a constant. And so here y squared is a constant, and we're just trying to integrate x squared plus, or x over x squared plus 1 times a constant. And we know how to do that. We can say u is equal to x squared plus 1. And so du is equal to 2x dx. And so 1/2 du is equal to x dx. And so we go ahead and substitute that in. This is an integral from -3 to 3. I'm going to factor out the 1/2. Okay. And let's see. When x is 0, u is 1. When x is 1, u is 2. And this is y squared over u du dy. Okay, now we can actually do the u integral. This is 1/2 integral from -3 to 3 of y squared times integral of 1 over u is a natural log of u. So that's ln of 2 minus ln of 1 dy. Ln of 1 is 0. Ln of 2 is just, we can factor that out of the integral. So this is 1/2 natural log of 2. Integral from -3 to 3 of y squared dy. And now we just do that integral. So this will be 1 over 6 ln of 2 times 3 cubed plus 3 cubed, I think. And if we work this out, I think this will be 9 ln of 2. Okay. So that's that one. It's just doing the integrals. I may have made a mistake there, but I don't think I did. Hopefully that one's okay. Let's move on to number 4. Find the volume of the region bounded above by the elliptical paraboloid and below by the square. Okay, so whenever we have a problem that's set up like this, we are going to start by integrating over our square, because that's the region of the xy plane, and so that'll give us the bounds on our integral. So that'll be, I'll do x here, and then y here. And then the thing inside the integral is the height of the region that we're trying to find the volume of. So here the height is just the paraboloid. That's 16 minus x squared minus y squared. And then it doesn't matter whether I do dx dy because they're the same. Okay. So now we just do the integrals one by one again. So I'll do the first integral with respect to x, treating y as a constant. So that's 0 to 2 of 16x minus 1/3 x cubed minus xy squared. And then x goes from 0 to 2. I'll write x here to indicate that. Now I'll plug in my bounds. The 0 one goes away, so I just get 32 minus 8/3. That's a very ugly 8/3. Minus 2y squared dy, which is 32y minus 8/3 y minus 2/3 y cubed, as y goes from 0 to 2, which is 64 minus 16 over 3 minus 16 over 3. And I'm just going to leave the answer like that. If you should probably simplify it on an exam, or we'll have to take off points. Unfortunately, I don't like that, but that is the policy. But I don't really want to simplify that. Okay, number 5, use Fubini's theorem to evaluate this integral. So whenever it says use Fubini's theorem, typically that means that the order of integration they give us isn't very good. And we can just sort of look at this for a second. Here we have an x here, and we have an x up here. And so if we were to do the integral with respect to x first, which is how it's set up, we would have something like x e to the x. And if you remember from Calc 2, to integrate that, you need to use integration by parts. Fubini's integral theorem is nice here because if we do y first, this is just a u sub because there's only a y up here, not in front of here. And so that's why we're going to do Fubini's theorem. So I'll swap the bounds of integration. X e to the xy dy dx. And now I can go ahead and set up this integral just like, or I guess in the other direction to make it easier. Remember, inner integral, x is a constant because we're integrating with respect to y. So I'll say u is equal to x times y. And then du, remember x is a constant, so this is x dy. Well, look, we have an x dy right here. And so this is going to be integral from 0 to 3. Integral, okay, when y is 0, u is 0. When y is 1, u is x. And then this is just e to the u du. Because xy is equal to u. Yeah, okay, that looks right. So now I'm going to integrate e to the u. I just get e to the u. Just integral from 0 to 3 of e to the u. U going from 0 to x dx. So that is integral from 0 to 3 of e to the x minus 1 dx. So now we just integrate this one more time. This is e to the x minus x from 0 to 3, which is e cubed minus 3 minus e to the 0 minus 0. If we work that out, that is e cubed minus 4. Okay, so that one again, just doing the integrals, probably a good problem to know how to do. I think we can move on. I'm going to do the challenge problem now. It's a bit annoying to do all the integrals, but if you're I want people interested to know how to do it. So let's see. I'm going to do the first one first, and I'm going to show all my steps on this first integral, and I'm not going to show as many steps on the second integral. Because it's a very similar integral. Okay. So let's go ahead and start this. It tells us to use one of these two trig substitutions. Remember, when I am doing this inner integral, I'm treating x as a constant and I'm integrating with respect to y. So I want to substitute y as something. And it tells me to do y equal to x tan theta. Then I find dy. Remember, again, x is a constant, so this is just x secant squared theta d theta. Okay. So now this will be integral from 0 to 1. I'm going to keep the 0 to 1 in terms of y, and I'll just substitute it back in later. Okay, let's see. So this is x squared minus y squared is x squared tan squared theta. In the denominator, the reason that this substitution was useful is because this will become a trig identity, but I will show that step. X squared tan squared theta squared. And then dy is x secant squared theta d theta dx. Okay. So now at this point we have to do some simplification. The first thing we might notice is that there's a trig identity that tells us that 1 plus tan squared theta is equal to secant squared theta. This is one of the trig identities that I told you on like the first week of Studio would be good to remember. And this is why it comes up a lot at this point. And so we can rewrite this integral 0 to 1, integral y equals 0 to 1. The reason I write y equals here is because I'm integrating with respect to theta, but my bounds are still in terms of y, so it just helps for clarity. But anyway, okay, so I'm going to factor all my x's out. From the numerator here, I will get an x squared. So I'll go ahead and match that. From the denominator here, I will get an x to the 4th. And then from the dy here, I'll get an x. Okay, so those are all my factors of x. I'm going to multiply by 1 minus tan squared theta divided by secant to the 4th of theta times secant squared theta d theta dx. Okay, and so now I'm going to bring the 1 over x out in front because it's a constant with respect to theta. That's the whole point of doing this. We're treating x as a constant. Then integral y equals 0 to 1 of, okay, let's see. So 2 of the secants canceled out. So that's 1 minus tan squared theta over secant squared theta d theta dx. Now we have to look at that integrand. We can split up the fraction. 1 over secant squared theta is equal to what? Cosine squared theta. And tan squared theta over secant squared theta is equal to, let's see, tan is sine over cosine, and then secant squared is 1 over cosine, so this is sine squared theta. All right, so this is integral from 0 to 1, 1 over x, integral y equals 0 to 1, of cosine squared theta minus sine squared theta is just cosine of 2 theta, d theta dx. And so now at this point we can actually integrate this using a u sub. This is integral from 0 to 1, 1 over x, times 1/2 sine of 2 theta, but 1/2 sine of 2 theta is just sine theta cosine theta, as y goes from 0 to 1 dx. Okay, and now I have to use a right triangle to figure out what sine theta and cosine theta are. So let's see, I initially said that tangent theta is equal to y over x. Tangent is opposite over adjacent. So we use the Pythagorean theorem. This is x squared plus y squared. And so sine theta is equal to opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. And so this is equal to integral from 0 to 1 of the this x. No, I don't like that color. This x and this x cancel out. And so we just get y over square root x squared plus y squared as y goes from 0 to 1 dx. Oh no square root because there's 2 of them. Okay. And so now at this point we can plug in the boundary terms. The y equals 0 one goes away. And then this just becomes integral from 0 to 1 of 1 over x squared plus 1 dx. Okay, you may remember that integral of 1 over x squared plus 1 is arctan. So that is arctan of 1, which is pi over 4, minus arctan of 0, which is 0. So this is pi over 4. Okay. So that's that integral. It's a bit ugly. Now let's start doing the other one, and then we'll see quickly. We'll take, after like a step or two, we'll take a shortcut to finish it. Okay. So it's the same thing, but we're reversing the order of integration. Duplicate that. And then we want to take x is equal to y tan theta this time because the order of integration is opposite. And so this inner integral, we're treating y as a constant. We're integrating with respect to x. So treating y as a constant, this goes with dx equals y secant squared theta. And so just like last time, integral from 0 to 1, integral x goes from 0 to 1. Of this time, we plug in this thing first. So we get y squared tan squared theta minus y squared all over. The bottom is going to simplify exactly the same. So it'll be y to the 4th secant to the 4th of theta, just like before. And then dx is y secant squared theta d theta dy. Okay? Again, I'll factor out my y terms. I'll get a 1 over y, just like last time. And this is integral as x goes from 0 to 1 of, let's see, it'll end up being sine squared theta minus cosine squared theta, which is, or actually here, what I'll say is this is tan squared theta minus 1 over secant to the 4th of theta d theta. And so at this point, you'll remember we already did this integral. We found out what this integral was equal to, so I'm going to skip all of those steps and just say, oh, this was integral from 0 to 1 of 1 over y times, the only difference is that there's a negative sign, so I'll put that out in front, just because instead of 1 minus tan squared theta, we have tan squared theta minus 1. Otherwise, it's exactly the same, sine theta, cosine theta, as x goes from 0 to 1. Okay, and again, sine theta and cosine theta are going to be swapped, but their product is going to be the same, and so this is going to be negative integral from 0 to 1. Again, I said I would be skipping some more steps here because it's very similar to the other one. And this goes from x equals 0 to 1. And so now again, these two, oh, that is way bigger than I want you to be. That y and that y cancel out. And so, and then the other x's we can plug in the boundary terms. So this is negative integral from 0 to 1, 1 over 1 plus y squared dy, which will give us negative pi over 4. Okay, and if you look at that, here we got pi over 4, here we got negative pi over 4. Those are not the same. And so you may say, wait, now hold on a second. Fubini's theorem says that we can swap these two bounds of integration. We can swap the x and the y, and it doesn't matter. And that's not quite what Fubini's theorem says. Fubini's theorem says that if these functions are continuous over both of these rectangles, then we can do that. These two functions are not continuous over that rectangle. In particular, they're discontinuous when x and y are both equal to 0. If x and y are both equal to 0, then we can't do this here. We can't divide by x squared plus y squared. And you could try to find the limit as x and y go to 0. And in fact, what you'll find is that one of them is positive 1. If you go from like this direction, the limit will be 1. And if you go from this direction, that's your origin, you'll get negative 1, which is exactly why these two were off by a sign, because one of the limits is 1 and one of them is negative 1. Okay, so that's that problem, and that's that whole worksheet. Hopefully that was okay. Hopefully having to do this twice didn't make me any worse at talking about it. As always, feel free to let me know if you have any questions about this.